Greetings, this is Professor Roman, and we are continuing our lectures on linear algebra. We're now ready to discuss inner product spaces. Throughout this discussion, the field F will represent either the real field or the complex field. Many common vector spaces possess an additional structure that is referred to as an inner product. You should be familiar already with at least one inner product, and that is the standard inner product or dot product on Rn. And it looks like this. If u and v are vectors in Rn, then the inner product uv, this is the notation we will use for inner product, the angle brackets with a comma in between. The dot product is sometimes denoted by u dot v as well, but I think we're going to avoid that notation. So the definition of the standard inner product in Rn is that u inner product with v is u transpose times v. You can't take the product of u and v as matrices because the dimensions are not correct. But if you take u transpose, you get a row vector, and then you can take that product with the column vector. So u transpose v, or equivalently v transpose u, and this is what it looks like. So it's the sum of the products of the corresponding entries. We need a couple of definitions in order to proceed without interruption. If A is an m by n matrices over F, and again F is either the reals or the complex numbers, the conjugate of the matrix A, denoted by A bar, is just the matrix formed by taking the complex conjugates of every entry in the matrix. The conjugate transpose, also called the adjoint of A, denoted by A star, is, just as it sounds like, the conjugate of A and then the transpose of that. So you take the conjugate and transpose the matrix, or vice versa. You can transpose first and then take the conjugate. Doesn't matter. For a real matrix, of course, taking a complex conjugate does nothing, and so this is just the transpose. A square matrix is self-adjoint, again a descriptive term, if it is equal to its own adjoint, or its own conjugate transpose. The basic properties of the adjoint are given here. This operation, the adjoint, is extremely important. A and B are two matrices of the same size. Little a is a scalar. Then the adjoint is additive. A plus B star is A star plus B star. Little a, capital A, so this is scalar multiplication. Take the adjoint. You can pull out the scalar, but you must make it the complex conjugate of A, little a, at times the adjoint of the matrix. For square matrices, the product AB adjoint is B adjoint A adjoint. This is just like a formula for the inverse. AB inverse is B inverse A inverse. If A is invertible, then the adjoint of the inverse is the inverse of the adjoint. This one is a bit technical, but will be useful. A transpose star, so star, remember, is both transpose and conjugate. two transposes will cancel each other, so this will just be A bar, the conjugate of A, and that's the same as A star transpose. The adjoint is an involution. If you apply it twice, you get back to where you started. Proof of these is left for practice, left to you for practice. So that's the background information that we need, and we're ready to define the inner product. Let V be a vector space over F. Excuse me. Once more, F is either R or C. An inner product on V is a function of two variables. We use the angle brackets and the comma. The dots here are just placekeepers for the variables that map V cross V to the base field. And they have the following properties. Positive definiteness, and that means that for any vector little v, its inner product with itself is always non-negative, bigger than or equal to 0. And it's 0 if and only if v is the 0 vector. So v inner product with itself is always strictly positive as long as v is non-zero. Conjugate symmetry, if we reverse the roles of u and v, swap them, we take the conjugate. Of course, when F is the real field, then conjugates don't mean anything, and so the inner product is just plain symmetric in the two variables. Finally, inner products must be linear in the first coordinate, and that looks like this. Pay careful attention here. W is the same in all three places. You cannot change both coordinates at the same time. The second one here is fixed. This is linearity in the first coordinate. A real or complex vector space together with an inner product is called a real or complex inner product space. And as usual, we extend the notation a bit. If x and y are subsets of V, we can take their inner product. It's defined as the set of all individual inner products of a vector from capital X and a vector from capital Y. And as a slight simplification of the notation, the inner product of a vector with a subset of vectors is this set. So these are convenient notational extensions. Note also that a subspace S of an inner product space is automatically an inner product space under the restriction of the inner product of V to the subspace S. There's no closure issues involved here. We just simply restrict the inner product to the subspace. Note also that the positive definiteness in the definition implies that the inner product of a vector with itself is always real, regardless of whether V is real or complex. To say that a scalar is bigger than or equal to 0, it implicitly says first that it's real, because complex numbers are not ordered in this way. If F is the real field, then symmetry and linearity in the first coordinate will imply linearity in the second coordinate. And so the inner product is linear in both coordinates. This is linearity in the first coordinate. W remains fixed in the second coordinate. This is linearity in the second coordinate. W remains fixed in the first coordinate. So we have both of these for real vector spaces, real inner product spaces. These together are referred to as bilinearity. So the inner product is bilinear, linear in both coordinates. Separately, you have to fix one coordinate, then you can apply linearity in the other coordinate. On the other hand, if f is complex, then the inner product is additive in the second coordinate, and here is the computation which you should do yourself. But as for homogeneity, when you have a scalar multiple in the second coordinate and you go through the computation, what you have to do is swap these two so you can take advantage of linearity in the first coordinate. You put a conjugate over there, pull out the a, separate, and so a scalar comes out of the second coordinate as its conjugate. This is referred to as conjugate homogeneity as opposed to ordinary homogeneity. And because of the fact that the complex inner product is additive, linear in the first coordinate, additive and conjugate homogeneous in the second coordinate, we say that the inner product is conjugate linear in the second coordinate. Here's the official definition of conjugate linearity. It just means that it's additive, any function between vectors, this should be, complex vector spaces. Conjugate linear means it's additive and conjugate homogeneous. Pull out the scalar, it becomes its conjugate. Because the inner product is linear in the first coordinate and conjugate linear in the second coordinate, it is referred to as sesquilinear. Sesqui means 1.5 times, so that kind of fits. Sesquilinear means linear in the first coordinate, conjugate linear in the second coordinate, 1.5 times linear. I wouldn't use that term. It might be confusing, but sesquilinear shouldn't confuse anyone. Just for a little practice with sesquilinearity, I suggest that you take this inner product, AU plus BV inner product with CX plus DY, and expand it before you look at my expansion here, just for some practice. Let's look at some examples of inner product spaces. We've already discussed the standard or dot product on Rn. Looks like this. And so Rn is referred to as Euclidean space, as we've discussed before. Unitary space is Cn. The standard, I don't know where that came from. The standard inner product on Cn is given by, rather than U transpose V, it's U transpose V conjugate. And so when you compare this sum with this sum, you see that they're very similar, but you have to take the complex conjugate of the second coordinates. This is unitary space. Something to note even now that will be important later, it's not complicated. If A is an n by n matrix, and we take the inner product of AU with V, that is V star AU, that's one way to describe it. It's this way here. And that can be written this way, the quantity A star V star U, and that is equal to this by definition, U A star V. So what has happened is that if you want to move the matrix across the comma, you can do so. You change it to its adjoint. This is a very useful formula. We will use it many times. And because adjoint's involution, we could replace A here by A star and get this formula. So in words, we can move A across the comma in either direction as long as we turn it into A star. In particular, if A is self-adjoint, then we are free to move the A back and forth across the comma without any changes. And we'll have much more to say about all this in the future. The vector space CAB of continuous complex valued functions on the closed interval AB is a complex inner product space under this inner product. You take the inner product of the functions f and g is the definite integral from a to b of f times g bar. And I'll let you confirm that's an inner product. Another very important class of inner product spaces for applications, especially, not only in mathematics but in the sciences, are these polynomial inner product spaces, r square bracket x, with a weighted integral inner product. The inner product of these two polynomials p and q is the definite integral from a to b of p of x, q of x, times a weight function, wx, which is fixed. And we'll come back to look at this again later with some specific examples of weight functions. We'll look at the Hermite polynomials, the Laguerre polynomials, the Legendre polynomials, all very famous sequences of polynomials using different weights. The vector space of all infinite sequences over F that have finite support is an inner product space. The inner product of two sequences is this infinite sum, Sn, Tn bar. But because the sequences have finite support, this reduces to a finite sum. All but a finite number of the terms are zero. So we don't have to worry about convergence. One of the most important inner product spaces is the vector space L2, we've seen before. In this case of all real or complex square summable sequences. This is what it means to be square summable. The sum of the squares, the norm squared of the terms is finite. And this is the inner product. Okay, same as up here. Same inner product, different inner product space, of course. These sequences are called square summable. I've already mentioned that, so I guess I don't need this. And of course, for this inner product to make sense, these infinite sums must converge. And this is the reason they converge. This inequality tells us that if the sums of these two terms are finite, then the sum of this is finite. So this is absolutely convergent. finally, the Hadamard product of two matrices of the same size is what maybe students might think the real product, the ordinary product of matrices should be, and that is you just multiply corresponding entries. So this is the analog of matrix addition. This is not nearly as useful as the ordinary matrix product, but it has an occasional use. If we denote the sum of the entries in any matrix by S of that matrix, then the sum function applied to the Hadamard product will look like this, and this is in fact an inner product on the square matrices. Let us now take a bit closer look at the inner product structure. One of the ways, speaking in general terms, one of the ways to advance a mathematical theory is to look for analogies or similarities, and to ask questions related to those similarities. So, for example, we have discussed the fundamental theorem on linear transformations, and we know that a linear transformation, tau, mapping V to W, is completely determined by its value on a basis for V. And those values can be specified any way we wish and extended by linearity to a linear map from V to W. This was critically important, which is why I called it the fundamental theorem on linear transformations, although I don't know whether anybody else does that or not. Well, now that we're dealing with inner products, we might ask, is there something similar to the fundamental theorem on linear transformations? So suppose that V is a finite dimensional vector space and that B is an ordered basis. We can ask the following questions. Is an inner product on V completely determined by its action on the basis vectors? That is to say, by this family of inner products, VI inner product with VJ. That would have an affirmative answer in the case of linear transformations. They are completely determined by their action on a basis. Secondly, can we define an inner product on V by giving these values any way we want? These are scalars, of course. Can we just assign these values any way we want? And if not, what constraints are required so that these values will define an inner product? That corresponds to the second part of the fundamental theorem of linear transformations. There's a third question which is unrelated to the earlier theorem on linear transformations. Since the coordinate map is an isomorphism, it seems as though the inner product UV of two vectors in the vector space and the standard inner product of their coordinate vectors might somehow be connected. So the question is, how are they connected, or are they connected? They certainly can't be equal, because the standard inner product doesn't depend on the inner product on V. we have to be a little careful about the notation here. The angle brackets here, because these are elements of Fn, refer to the standard inner product. It might have been a good idea for me to use a subscript S or something, but you won't see that too often, so I didn't do it. These angle brackets refer to the inner product defined on the vector space V. As far as question 1 is concerned, is an inner product completely determined by its action on a basis? I'm going to leave that for you to show that, yes, it is indeed completely determined by the action on a basis, and that's just pretty much direct consequence of the sesquilinearity of the inner product. To deal with the other two questions, we need a definition. It's best to place these inner products, which are two-dimensional, as I and j both vary from 1 to n, into a matrix. So, V is a finite dimensional inner product space, and B is an ordered basis. The gram matrix of the inner product space V with respect to this particular basis is this matrix. I will denote it by capital G sub B, and the entries are G sub ij, and notice that G sub ij is the inner product of Vj and Vi. So there's a switch in the indices here. G sub ij is Vj, inner product Vi. You can't interchange these two unless you have symmetry. So in general we don't, so we have conjugate symmetry. So this has to be done carefully here. There's a reason for doing this, why the ijth entry of the gram matrix is Vj inner product Vi, and it will appear in a little while. So you'll see why it's done that way. So the gram matrix then uniquely determines the inner product because it's simply a convenient way to give us all these inner products of the basis vectors. And as I've said, I'm leaving it to you to show that those inner products completely determine the inner product. So we can rephrase this second question. Can we define an inner product by giving these values any way we want in terms of the gram matrix? How can we characterize gram matrices? Which n by n matrices are the gram matrix for an inner product under some ordered basis? If the answer is all matrices, then the answer to number 2 is yes, we can assign the values any way we want. But you might have guessed already, this is going to be false. We don't have a perfect analog with the fundamental theorem on linear transformations. Well, there are requirements for an inner product, such as conjugate symmetry and linearity in the first coordinate, and they're going to put some constraints on which matrices can function as gram matrices. The conjugate symmetry will tell us the following. G sub ji, that's the ji'th entry in the gram matrix, is by definition Vi inner product Vj, and by conjugate symmetry, that's the conjugate of Vj inner product Vi, and that is the conjugate of the ijth element of the gram matrix. So what this tells us is that the Graham matrix must be self-adjoint. The conjugate, it must be equal to its own conjugate transpose. To go from here to here, you'll see the conjugate and the transpose. So, at the very least, the matrices that function, provide us with an inner product, the inner product of the basis vectors, and therefore the entire inner product, at the very least must be self-adjoint. But there's more going on. So we need to look a little bit more. And we also need to deal with the third question. So if we jump ahead to that, it'll help us finish the second question. To connect the inner product UV with the standard inner product of the coordinate matrices, there's two ways we can proceed. One, you might say, is just brute force computation. And the other way is, well, at least less brute force, maybe elegant even. So let's look at both of those, beginning with the brute force approach. Starting with an ordered basis, and that's the one we have here, V is V1 through Vn. Suppose that a vector u is this linear combination of the basis vectors and v is this linear combination of the basis vectors. Then to make the connection between these two inner products, we start with the inner product of u and v, and that is equal to this. Just substituted these two linear combinations. The sesquilinearity allows us to expand this so that it looks like this. You can see the b scalars being in the second coordinate get conjugated, complex conjugated. And anyway, I'm not going to explain all the details of this computation. You should be able to do that yourself. And this can be written this way. Vi, inner product Vj, is the transpose of the ijth entry. Sorry, I didn't say that right. It's the ijth entry of the transpose of G. And that can be written this way, which then can be written like this. And here I have, because the notation is getting rather unreadable, I dropped the subscript b on the coordinate matrices. So this one is really should have a subscript b. So it's the b coordinates of u transpose. This is the b coordinates of the vector v bar. And that can be written this way, which finally can be written this way. And so we have this rather elegant formula. The inner product of u and v is the standard inner product of these two vectors. We take the b coordinate of u and the b coordinate of v, but we have to multiply the b coordinate of u by the Graham matrix. This makes sense, at least as in the sense that this side is going to have to involve something that comes from the inner product on V. If this matrix wasn't there, as I said before, these couldn't possibly be equal because this would not depend on the inner product on V. So this is the connection. It's the Graham matrix that allows us to make the connection between the inner product on V and the standard inner product on Fn. This is a very important formula. If you were going to do this in more detail, it would even be longer. This is the brute force method. But here's a more elegant way to proceed, and that's a matter of judgment, of course. If we take two basis vectors, vi and vj, then this inner product is the jith entry of the Gram matrix, which can be also written as an inner product of the ith column of the Gram matrix with the jth standard basis vector. That will pick out the jth row of this matrix. So we're picking out the jth row of the ith column of the matrix, in other words, little g, ji. And this can be written this way. The ith column of this matrix is just the matrix multiplied by E sub I, and E sub I is the same as the B coordinate matrix for one of the B vectors, V sub I. So this is a relatively straightforward computation, certainly simpler than all of this other stuff we did here. Now we come to the elegant part, and that is the B coordinate map is linear. As we know, it's an isomorphism. Multiplication by G sub B, by any matrix, is linear. The inner product is linear in the first coordinate. So we've got basically a composition of three linear maps going on here, starting with VI. We take its coordinate matrix, that's a linear process. We multiply by this Gram matrix, that's a linear process. We stick it in the first coordinate of an inner product, it's linear there. And so, for a fixed V sub j, that's the second basis vector, the map that sends x to this inner product, so I put an x here where vi was, one would say loosely that this is linear in V sub I. So this is linear in V sub I. This is a little bit more detail. The map that sends x to GB, B coordinates of x, inner product with B coordinates of Vj, is linear. And so we can replace x by any vector we want, and we have this equation. Now we can use the conjugate linearity of the inner product together with the linearity of the coordinate map to be able to replace Vj by any vector, and we get the same formula we had before. So I would recommend that you go through this proof again, try to duplicate it yourself, and think about this argument. This is a typical linearity argument, and it can save a lot of computation, and it can shorten proofs, but it takes a little while to become comfortable with it. But it is a clear demonstration of the power of linearity. This also makes it clear why we reverse the indices in the definition of the Gram matrix in order to get this formula. So this formula answers question 3. It gives the relationship between the inner product on V and the standard inner product of coordinate matrices. But it also contributes to question 2 regarding the requirements of a matrix for it to be a Graham matrix for some inner product. We've already seen that the conjugate symmetry requires that a Graham matrix has to be self-adjoint. But positive definiteness is going to add additional restrictions on the Graham matrices. If we set U equal V here in this formula, I wish this formula had a name, but as far as I know it does not. We get this, the inner product of U with itself, it looks like this. Positive definiteness then tells us that this is equivalent to this statement. UU is bigger than or equal to 0. In other words, this is bigger than or equal to 0 with equality if and only if U is 0. These are coordinate matrices, but as U ranges over all the vectors in V, these coordinate matrices range over all elements or all vectors x in Fn. So this translates into this equivalent. It's equivalent. GBX inner product x is bigger than or equal to 0. That's with equality if and only if x equals 0. This is the positive definiteness of the inner product, expressed in terms of the standard inner product, and involving, of course, then the Graham matrix. So this calls for another definition. A matrix, n by n matrix, is positive definite if it has two properties. It's self-adjoint and it satisfies this property we were just discussing. So the Graham matrix of an inner product is positive definite, self-adjoint, and has this additional property. And it also, of course, satisfies this nice formula. The converse also holds. If G is any positive definite matrix, we can use this formula that I just pointed to, this formula, to define a function of two variables. If G is any arbitrary matrix, we could still use it to define a function of two variables. But if G is a Graham matrix, this will in fact be an inner product. It'll be positive definite, because again, when we put U equals V, we get this, and it's conjugate symmetric, and here is the computation for that, which is something, again, you might want to try to do for practice. And finally, it's linear in the first coordinate by the same reasoning, actually, that led us to derive this formula. Where did it go? Right here. Okay. So now we've answered all three questions. And here is a summary. V is a finite dimensional interproduct space over F, and here's an ordered basis. A matrix A, n by n matrix, is the Graham matrix of an inner product on V if and only if it is positive definite. So loosely speaking, we can find all inner products on V simply by finding all positive definite matrices. Actually, simply is the wrong word because that's not so simple. But in theory, That's the connection. The Graham matrix map that sends an inner product to its Graham matrix. Now we've fixed an ordered basis, so that's part of the map. Gamma sub B. This sends an inner product on V to its Graham matrix with respect to B, is a one-to-one correspondence between the family of inner products on V and the family of positive definite matrices. An inner product on V can be expressed using the standard inner product on Fn by this beautiful formula. An inner product on V is completely determined by the values Vi, Vj, the inner product of the basis vectors. And these values can be assigned arbitrarily as long as this matrix is positive definite and therefore is a Graham matrix. Okay. I have a picture here. I don't know if it's very enlightening or not. Gamma sub B maps inner products to Graham matrices or to positive definite matrices. Choose a different ordered basis, you get a different one-to-one correspondence between the inner products and positive definite matrices. Example, here's the standard basis for the complex polynomial space C2 square bracket x. And here is a complex matrix. This matrix happens to be positive definite, and we'll discuss the reasons for that, how I know that a bit later. It's certainly easy to check that it's self-adjoint. If you take the transpose and the conjugate, you're going to get the same matrix. The other part is, of positive definiteness is a little more difficult, but it's just some algebra that you could do. You have to check that G, V, inner product V is always greater than or equal to 0, and only 0 when V is 0. So it's certainly doable. What's more difficult is where did this thing come from in the first place? Once you have a matrix, you can check it for positive definiteness, but where do you find positive definite matrices? That is quite tricky, and we will discuss it a bit later. Anyway, since this matrix is positive definite, it is a Graham matrix. It is, in fact, the Graham matrix for the standard basis. And so it defines an inner product. And this is the formula. So for example, if this is, you have two polynomials, P of x and Q of x, then the standard coordinate matrix for P of x is this, and for Q of x is this. And so when we use this formula, the inner product of P of x and Q of x looks like this, which computes to this, and actually gives you 7. Okay, so this matrix, being positive definite, defines an inner product with respect to the standard basis, or other bases too, but with respect, in this case, to the standard basis. And this is how you compute with the inner product. You use this formula. Suppose we change the ordered basis. 1, x plus 1, x squared plus 1. Then G is the Graham matrix of an inner product on C2 square bracket x with respect to this basis and it's given by this formula. See, now I have basis B here. So if we again take these two polynomials, we're going to get different coordinate matrices because we are using a different basis. And so the inner product in this case comes out to be 1. That should not be a surprise. It's a different inner product. Okay. A change of ordered basis from, in this case, the standard basis to another basis changes the one-to-one correspondence. So the same positive definite matrix produces a different inner product. Well, now we come to this question, which matrices are positive definite? That's obviously now, in view of our discussion, rather important. And as I said, determining whether a matrix is self-adjoint is easy. We will see in chapter 8 of the book, quite some time to come, a self-adjoint matrix A is positive definite if and only if all of its complex eigenvalues are actually real and positive. Well, determining the eigenvalues of a matrix is in general not possible, so that's not directly as helpful as we would like it to be. As a matter of fact, as we'll see in chapter 7, self-adjointness itself guarantees that the complex roots of the characteristic polynomial, the complex eigenvalues, are in fact real. So all we're left with is the problem of determining whether those eigenvalues, the real ones, with any eigenvalues, then they're all real, are in fact positive. Since we can't in general compute the exact values, that won't help. But one approach would be to approximate the eigenvalues sufficiently, with sufficient accuracy, to make that determination. Are they positive or not? And that's not an unreasonable approach, but it is outside the scope of this book and the lectures that I'm giving. On the other hand, there are times when we can determine whether or not a self-adjoint matrix has positive eigenvalues without actually computing or even approximating those eigenvalues. This is a subject that we will cover in chapter 12 of the book. It's one of the topics chapters. And if I still have any energy left when I'm done with the core portion of this course, I'll go over this material. Part of it is going to depend on how popular these lectures are, whether there's any real interest in these lectures, as to how much I do beyond just the absolute core material. Actually, I've already gone beyond some of the core material in our discussions. I certainly covered more preliminary material than you find in any book on linear algebra, at least not to my acquaintance. As a matter of fact, while I'm on the subject, I took a look in some of the more popular linear algebra books, undergraduate books, at least in my area of the world, and they don't even mention Graham matrices. They're not in the index anyway. I haven't paged through the whole book in both cases, but that's a little surprising to me. You know, there is the issue of time. The books are generally tied to courses, and courses have limited time span. But I think this is really important, and it's important for its own sake, but it's also important for what I said at the beginning of this lecture, and that is we're making a connection here. if you were the first to study inner products, and you sat down and you decided, I'm going to develop the theory of inner products, one of the questions that would come to your mind is the three questions that I gave at the beginning of this lecture, or put another way, it seems like there is a familiar pattern here that we developed for linear transformations, and it led to the fundamental theorem of linear transformations. What's going on in that regard with respect to inner products? So the Graham matrix naturally appears when we try to answer those questions. And this is how mathematics works. This is how mathematics is created. Very few things are created in a vacuum. That works that way in other subjects too. If you listen to classical music, when you listen to early Beethoven, it sounds a lot like late Mozart. Anyway, that's getting off the subject. Here is a theorem that we're going to come to in chapter 12. Let A be a real matrix with the property that all of its principal minors are non-zero. I'll give you an example of this in a minute. Then A can be reduced to row echelon form, which we'll call R, using only elementary row operations. No scaling of rows, no interchanging of rows. Only using only elementary row adjustment operations. And that's what these are. Row J is replaced by row J plus a scalar multiple of row I, where J is bigger than I. This is the operative thing here. J is bigger than I. In other words, a lower row in the matrix is adjusted by adding to it a non-zero multiple, otherwise we're wasting our time, of a higher row in the matrix. So these are specific row adjustment operations, which I will call downward row adjustments. So we might take the 10th row and add to it a multiple of the 8th row or the 3rd row, something higher up in the matrix. Okay. So a real, did I say symmetric? I hope I did. A real symmetric matrix with the property that all of its principal minors are non-zero can be brought to row echelon form using only, not only just row adjustment. You know, there are 3 row operations, right? Interchanging rows, scalar multiplying rows, and these row adjustments. Not only using only row adjustments, but only specific ones, downward row adjustments. Now here's the point of this. The matrix A is positive definite if and only if the row echelon form of A that is obtained using, I think I should say only, downward row adjustments has only positive diagonal entries. Example. Here's the matrix from before. We can proceed in a couple of ways to show this is positive definite. It's a self-adjoint, so we don't have to worry about that. The characteristic polynomial is this cubic, and these are its roots. All of these roots are positive, so matrix is positive definite. And again, that's stuff we'll discuss in later chapters in detail. But that we were lucky here that we could solve, this was only a cubic and we could solve it. If this had been a larger matrix, this approach would fail probably most of the time. The alternative is to apply this theorem. So we look at the principal minors. We take this determinant, we take this determinant, we take the whole determinant of the whole matrix. These are the principal minors, 2, 3, and 4. And we can use, so these are all non-zero. That's part of the requirements of the matrix in order for this theorem to hold. It's real, it's symmetric, and all its principal minors are non-zero. So all these principal submatrices are invertible. And we can use the 2 downward row adjustments to bring this matrix first to this one, and then finally to this matrix, which is in row echelon form. Just got to make sure here I didn't say reduced row echelon form, because that would be a disaster. Row echelon form, good. Okay. And the entries on the diagonal, they're all positive. Therefore, the matrix is positive definite. So, again, we were lucky that the first, the matrix was small enough and the characteristic polynomial was easy enough to deal with. But in general, that won't be the case. And yet, this other approach would be much friendlier in other circumstances. Okay, so this theorem is quite valuable with respect to spotting positive definite matrices.